Hello everyone. In this segment, we shall see some design concepts of pumps and allied theories and numerical problems related to the design of conveyance systems. Some basic inputs, head power and efficiency relations. When it comes to a pump and pipe systems, total head to which the pump should work should be equals to suction head plus delivery head plus losses. All these things are expressed in terms of meters, or in turn H is equals to HD plus HS plus HL. Most of the times we consider only the major losses here. Work done by the pump is gamma into Q into H, which is expressed in terms of watts, divided by 1000 will give you the values in terms of kilowatts. Watt horsepower WHP is gamma QH divided by 0.735. This is to convert from watts to horsepower, and 1 horsepower in a way is equals to 735 watts, or also equals to 0.735 kilowatts. This is the thing which is used here. And if eta is the efficiency of the pump set, we can also calculate brake horsepower of the pump. We call it as BHP, and BHP is equals to water horsepower divided by efficiency. Watt horsepower is expressed in terms of kilowatts divided by efficiency into 0.735. So it's about gamma QH divided by efficiency into 0.735. With this backdrop, let us solve a numerical problem related to the design of conveyance systems. Here comes the problem statement. Water has to be supplied to a town with 1 lakh population at the rate of 150 LPCD. LPCD stands for liters per capita day from a river 2000 meters away. The difference in elevation between the lowest water level in the sump and the reservoir is 36 meters. If the demand has to be supplied in 8 hours, determine the size of the main and brake horsepower of the pumps required. Assume maximum demand as 1.5 times the average demand. Assume F equals to 0.0075, velocity in the pipe 2.4 meter per second, and efficiency of the pump is 80 percentage. Now there are a few very important things are given as a data here. Population is given, and for 1 lakh population LPCD liters per capita is given, length is given, the suction head as well as delivery head is also given as 36 meters, and all these things have to be supplied in 8 hours. We are supposed to calculate the size of the main diameter and brake horsepower BHP of the pumps required. And to calculate all these things, an assumption can be used here, and that is the maximum demand is 1.5 times the average demand. Some sort of a peak factor here it is. And to calculate the head losses, the major head loss specifically, we can make use of F. F equals to 0.0075. F is coefficient of friction here. And velocity to calculate the diameter is 2.4 meter per second, and efficiency which is required while you calculate the brake horsepower is 80 percentage. Now with this, let us proceed with the solution part. Population is 1 lakh and per capita demand is 150 LPCD. Now let us calculate the average daily demand from these two values. It is 1 lakh into 150 liters per day. LPCD is liters per day. So the average daily demand is around 15 into 10 raised to 6 liters per day, or it is 15 million liters daily, MLD, 15 MLD. And as per the assumption which is given here related to the peak factor 1.5, maximum daily demand is 1.5 times the average daily demand. Average daily demand which we have calculated in the last step is 15 MLD. So by multiplying 1.5, it's around 22.5 million liters daily. Remember, it is million liters daily. The pump has to work for 8 hours a day. Capacity of the pump to be calculated for only 8 hours. Remember, we are not calculating for whole of the 24 hours. Pump will be in a functioning form or in its lifting process only for 8 hours a day. So it is 22.5 into 24 by 8. 24 by 8 is that fraction of time for which the pump will lift water. So it is around 67.5 million liters daily. So we had a 22.5 million liters daily, and if it was supposed to be lifted only 8 hours daily, so it is 67.5 million liters daily. And the next one is we calculate discharge here. Discharge per second. Million liters daily is also a discharge, but it is not expressed in meter cube per second. Let us try to express in terms of meter cube per second. 67.5 million liters, million 10 raised to 6. So it is liters divided by 10 raised to 3 to convert itself into meter cube, and it is daily. So let us convert a day to seconds. So it's 24 into 60 into 60. So ultimately we have a value in terms of meter cube per second for discharge Q, and that is 0.781 meter cube per second. So V is 2.4 meter per second. We know the concept of continuity equation, and it says Q equals to area into velocity. Okay, so area required is calculated as Q divided by V, or I hope you know that Q is equals to area into velocity. So Q is 0.781 meter cube per second divided by the velocity 2.4, and area required is 0.325 meter square, 0.325 meter square. We all know that we design a pipe with a cross section to be equals to a circular. A cross section would be always circular in most of the cases. So for a circular cross section pipe, area is equals to pi by 4 d square, or area is 0.325 here. With this relation, we could able to calculate d. So d is 0.643 meters, or let's say 0.65 meters for the design purpose. So the total lift is Hs plus St plus head loss, but from the data Hs plus St is given. So the rest of the job is to calculate head loss. So suction plus delivery head, which is given in the problem statement, is 36 meters, and head loss HL is 4FLV square by 2GD, the famous Darcy-Weisbach equation. So F here is given as 0.0075. L is 2000 meters or 2 kilometers. We use in terms of meters 2000 meters. Velocity is 2.4 and diameter is 0.65. We substitute all the values here, and HL calculated is 27.1 meter. Now we can calculate total lift. Total lift is 36 meters Hs plus St plus head loss plus 27.1, and it is around 63.1 meters. H is 63.1 meters. Brake horsepower of the pump is WHP divided by eta. Strictly we say this WHP should be in kilowatts. Then only you can substitute the horsepower, this value equals to in kilowatts. Instead, you can also substitute this as 735 if you keep gamma QH in terms of watts. So gamma is 9810 into 0.781 into 63.1 divided by 1000, and whole divided by 0.735 into zero point 0.8. So that is divided by 1000, which is missing. I hope you can also understand this equation as 9.81 into 0.781 into 63.1 divided by 0.735 into zero point 0.8, and the final answer for the brake horsepower of pump is 822 horsepower. I hope you have understood this. We just have designed a pipeline with the population 1 lakh and liters per capita daily is 150. and the diameter designed is around 0.65 meters, and the brake horsepower is 822 horsepower. Thank you.